In this video, we're going to talk about instantaneous velocity. This is really just an application of what we've talked about before. In the previous video, we talked about the slope of the tangent at one particular point was the instantaneous rate of change. When we have a position or a distance function, this concept is giving us the average rate of change in the distance, or an average speed or velocity, and as we approach one certain point in time, it's going to give us an instantaneous velocity. So if you think about the speed of your car, whenever you look down at the speedometer, that's an instantaneous velocity. You're not finding the distance elapsed between 2 points in time and performing a division. You're seeing exactly how fast you're going at that particular point in time. So in this class, what we're going to do is looking at the average velocity turning into the instantaneous velocity of a position function relative to time. So it's common to call a position or distance function S, and then the independent variable is t. So this graph is the graph of a position function, the function 4.9t squared, which describes the distance an object in free fall has fallen after t seconds, so the distance in meters. So for instance, this point represents after 1 second, the object has fallen 4.9 meters. After 4 seconds, the object has fallen 78.4 meters. So the average velocity between 1 and 4 seconds is just the average rate of change of this function. So in this case, if I find the average rate of change between t equals 1 and t equals 4, I get 24.5 meters per second. So like we did before, we're going to be moving a point closer and closer to a certain point in time. So here we've gone from 1 to 4 to 3.9 to 4. And doing the same thing, figuring the average velocity, which is just the average rate of change of a distance or position function. I'm doing the same thing I did before, but with t equals 4 and t equals 3.9. And now I see the average velocity between these two values that are closer together, so I have a smaller time interval, is 38.71 meters per second. So I've gone from an estimate of 24.5 meters per second between 1 and 4 seconds to an estimate of 38.71 meters per second between 3.9 and 4 seconds. So instead of looking at particular values on a function, we want to generalize this and find a general formula for the instantaneous velocity for this function. So instead of picking 4 or 1, I'm going to say, okay, let my constant point in time be a. And I'm going to look at smaller and smaller intervals from that time a. So here is the interval from t equals a seconds to t equals a plus 1 second. So this is my average rate of change formula when I use this function. And notice it results in 9.8a plus 4.9. Now when I go from the interval a to a plus 0.5, and I put those two values in the average rate of change function, I get 9.8a plus 2.45. And again, with even smaller interval of a to a plus 0.25, so here I have a quarter of a second interval, I plug those values into my average rate of change function, and I get 9.8a plus 1.225. So notice this thing that is being added to 9.8a is getting smaller and smaller, but 9.8a shows up in each computation. So it's safe to say that the closer we get to a, these remainders are going to be approaching 0, and the formula for the instantaneous velocity is simply 9.8a. And we'll see in the next couple of sections how to generalize this even further. So for example, if we plug t equals 4 seconds into our formula, this gives us an instantaneous velocity of 39.2 meters per second, which is pretty close to that approximation we got before. So in summary, the instantaneous velocity is really just an application of going from the average rate of change of a function, in this case a particular type of function, a position or distance function, to the instantaneous the instantaneous rate of change or instantaneous velocity.